Welcome back to the 12th part of Debugging at Scale, where we pull out the bug with fine-grained tweezers. Debugging is the process of constantly narrowing the problem space until we find the root cause. We circle the bug by defining its quadrants. Then we use the process of elimination and carefully crafted experiments to circle the bug, much like a hunter and its prey. This process is dangerous since we need to make assumptions about the code. In most cases where debugging fails and takes longer than expected, it is due to wrong assumptions. A mistake in this stage can drag the debugging session much longer than a mistake in any other stage. I love the show Dr. House. It's a Sherlock Holmes version of a medical drama with a grumpy misanthrope as the lead. Perfect. Medicine isn't like software debugging in most ways. We can replicate problems without hurting people. We can be very invasive without repercussions. We can conduct our own tests and get results instantly. But there's still a lot to learn. And one of the core tenets of the show is that everybody lies. People tell partial stories and miss crucial information for various reasons. This is a very common problem for debugging. The hardest bugs are often the ones where we spend most of our time on a wild goose chase. The reason for that is usually a lie or a misdirection because of a faulty assumption. The solution to wrong assumptions is double verification. For every assumption, no matter how basic, find another approach for proof. Let's say we have a bug in the code that depends on a result from a remote service. We assume the service works correctly, and we verified that by using the curl program. To double verify, we also need to add a trace point in the code that shows we received the response. As we slowly narrow our assumptions, we don't need to double verify every assumption. But if we feel the process is stuck, we need to go back and make sure that we verified every stage along the way. It's often the case that we miss something silly or simple. Make sure you verify the low-hanging fruit first. Sometimes double verification means stepping outside of the debugger. I'll discuss some external tools for debugging in the next module. These tools let us verify that the application is accessing the resources we expect on the operating system level. A company contacted me to help improve their process performance. In the morning meeting, everyone spun up theories about the system, which I didn't know at all. Every single assumption was wrong. Profiling revealed the truth. Assumptions are guesswork. Thankfully, we have tools that can instantly point at the facts. We can look at debugging as a process of hypothesis, prediction, and forming an experiment to prove the hypothesis. Assumptions fit into the hypothesis stage, where we form the boundaries around the bug. Another approach is one of hunting. Imagine setting up a fence to trap a predator within the fence. The biggest mistake you can make is a fence that's too small. Such a fence could leave the predator outside. You will be on the inside of the fence, wasting time searching within the confines of an empty fence. The inverse is just as bad. When you fence off a large area, it will take a great deal of time to narrow down on the predator. This is our application. This is the symptom we see. the thing that made us assume there's a bug in the system. To make matters worse, the bug might be in a different area altogether, since the root cause and the bug aren't necessarily the same thing. Let's give an example. A user sees the wrong time when adding an entry to the system. That's visible in the user interface in one end of the system, but the root cause is due to a bad time written to the database. The bug itself is due to miscalculation of daylight saving time. We need to make basic assumptions, but we don't need to verify every little thing. It's hard to quantify the right amount, and this is where experience makes a difference. Awareness and methodology help boost that experience. We need to decide where to place our assumptions. If we focus on the symptoms, we will need to grow our assumption perimeter. And if we place it too widely, we'll need to narrow it. We can waste a lot of time by checking inconsistently and moving in the wrong direction. Locating the bug or even fixing it aren't our goals when debugging. Understanding why the program behaves the way it does and the root cause for that is the ultimate goal. That isn't always an attainable goal, as the track might run dry, but we can leave traps for the next time and lay the long-term groundwork. I have more to say about defensive coding in an upcoming module. Our crash reporting solution would periodically send us null pointer exceptions that shouldn't happen. They happened in production on cases we never physically saw and had no access to. We tried multiple workarounds for the symptoms, but they just made the problem worse. By placing elaborate logging on code that we assumed worked correctly, we were able to find an edge case race condition when dealing with native code. When we see a symptom, we need to prioritize the symptoms we make to find the root cause. Normally, we use our intuition and experience to guide us toward that root cause. But is there a better way? We often make a shortcut, trying to get from the system to the root cause. That's often misleading. Our focus should be on the next stage, which is the bug itself. Once we understand that the journey to the root cause is hard, but we have better tools to do that. When working with a wide assumption perimeter, intuition is the only guide. However, when circling the symptom, initial assumptions often become obvious. If a value is incorrect on the screen, we can start by verifying that the source returns the right value and work our way from there. Sometimes we're left with a value that shouldn't be here. This can be a variable value, a UI element, or any other artifact. It's a value that doesn't make any sense, and we don't understand how that value returned from this method at this point. We might not have an immediate move that we know something is clearly wrong, but we don't know how it got to that point or where the data came from. If this is something you can reproduce and the data is in a field, then a well-placed conditional field watch point can be illuminating. This helped me solve many such issues in the past, but sometimes it just isn't enough. The issue might not be easily reproducible, and in this case, we might have a problematic state that's hard to investigate. This is one of the best scenarios for time travel debugging, which lets us traverse the state of the application after execution completed. If you're using a safe language, also known as managed languages, that's guarded against memory or stack corruption, then you have one option. Add trace points to every quarter and slowly expand the assumption scope in that direction. For unsafe languages, you will need to check the debugger capabilities of memory guarding or use a memory guarded allocator. A common mistake we make is rushing to the line of code that contains the bug, since we already know where the problem is. We then get settled into a specific area around the bug and waste a great deal of time looking at that code. We're trapped by the lure of a quick fix, which is incorrect, in which we incorrectly assume we know. Due to a distance between the symptom and the root cause, we might be misled by the lure of familiar code. We should first create a wider circle than we would expect by debugging the code we assume works correctly. When we do that, there are two eventualities. The assumption isn't working as expected. At this point, we can widen our search and might be closer to the solution. The assumption is working as expected. At this point, we can deepen our recollection of the code and understanding of the current application state. We have a solid base to proceed deeper. The scope should typically start at the next logical abstraction level. If the symptom seems to be related to a private method, start verifying the public methods. If a specific class is misbehaving, verify the classes that provide it with input. I usually give the analogy of a mechanic checking all the nearby screws are tight before dealing with the actual problem. A great example here is the invalid value of a field. Our initial assumption would usually be that we need better validation controls to stop the invalid value. This is probably bad input from the user that propagates all the way into the variable. Before we leap to that assumption, we need to verify that our code didn't propagate a bug onward. In the next video, we will discuss common problems and solutions which help put a practical spin on this theoretical high-level module. If you have any questions, please use the Slack channel to ask them. Thank you.